So, hi everybody. So this is our next seminar talk from the N3AS Summer Series seminar. And today we have Mukul Sholapurkar from UC San Diego. He is currently a postdoc of Tongyan Lin, actually, and before he obtained his PhD at Stony Brook. And so he's expert in dark matter and direct detection. So we'll be today talking about mu signals and backgrounds in direct detection experiments. So please, Mukul, go ahead.
Okay, yeah, great. Yeah, thanks, Lucas, and the organizers for giving me this opportunity. It's great to be here. Okay, so today I'm going to be talking about new signals and backgrounds in direct detection experiments. Oh, yeah, okay. Yeah, so just as a big picture introduction, so we know that there is very strong evidence for the existence of dark matter, but all this evidence is through the gravitational interactions of dark matter, and so naturally the big question is, does dark matter interact with standard model particles through any forces other than gravity? And we know several experiments over the last many years now, many decades, have been trying to answer this question in a variety of ways. Now, these different detection strategies that are typically used can be well illustrated by a diagram like this in this slide. So, assuming dark matter has some interaction with the standard model particles, we can collide two standard model particles together to produce dark matter. So this can be done in colliders, or dark matter particles can collide together to create a signal in the standard model sector. So this happens in indirect detection. Or finally, you can build a detector, and if a dark matter particle passes through, it can create a recoil or some sort of a signal that you can measure in that detector. So this is called direct detection. So in this seminar, I'm going to be focusing on this direct detection strategy to look for dark matter. So even within direct detection, there are various channels to look for dark matter, and they can be illustrated on a plot like this, which is an energy versus momentum plot, which I've borrowed from this paper. So on the y-axis is basically energy that the dark matter deposits in your detector in a single interaction. And on the x-axis is the momentum that the dark matter loses in this interaction. So traditionally, we have been looking for elastic nuclear recoils of candidates like weakly interactive massive particles, or WIMPs as they are called, which typically live above the GeV scale. So we have been looking for elastic nuclear recoils from these candidates. And for dark matter masses of GeV and above, this works really well. There are well understood radiogenic and cosmogenic backgrounds above keV scale nuclear recoil energies, which is the typical recoil scale for these masses. There are many giant detectors that have been built using noble liquids. They have their background models, they're very clean, and they have tremendous sensitivity. So that is a very nice picture above the GeV scale that we have. But as we go to sub-GeV dark matter, this particular channel of direct detection starts failing kinematically because the signal energy becomes too low to detect with current detectors. So to probe sub-GeV dark matter, recently in the last few years, experiments have been using electronic excitation. So to look for electron excitations induced by dark matter in their detectors. So typically, in these detectors, the signals are of the order EV scale, which are the typical band gaps of the semiconductors which are being used in these experiments. And to even go beyond MeV scale, to probe sub-MeV dark matter, there are no current experiments that do this, but it has been proposed that we can look for example, single phonon excitations or multi-phonon excitations. So phonons are nothing but collective excitations of nuclei that are excited by dark matter in crystals. So these signals will typically lie even below this EV scale. So these will be like milli EV or tens of milli EV scale signals that people will look for. So on the right-hand side, for these traditional detection methods, as I said, the backgrounds are really well understood above the keV scale. But on the left-hand side, where the signals are EV scale or the signals will be milli EV scale and so on, the backgrounds are not yet that well understood. And for the last couple of years, my collaborators and I have thought about this, and we have estimated backgrounds for both these cases for experiments that have run recently that have used electronic excitations to probe sub-GeV dark matter, and for experiments that will use phonon excitations to probe sub-MeV dark matter. So that will be the main subject of my seminar today. So I'll first start with some of the recent experiments that have looked for electronic excitations to probe sub-GeV dark matter. So for the theorists in the audience, why should we care about this? So if you see this plot of cross section versus the mass, so these are the constraints that are put by these recent experiments by looking for electron recoils in their detectors. And there are theoretically very well motivated targets in even in this sub-GeV parameter space. So I'm just showing one target here. So if you have fermionic dark matter interacting through an ultralight dark photon, then at these masses and at these cross sections on this line, you can generate the right relic abundance through the freeze-in mechanism. So this is a very nice theory target, and we would in principle like to probe this target in these experiments. And these experiments are trying to expand in their exposure and are trying to get sensitivity to lower and weaker interactions. But they could be limited in their sensitivities by backgrounds. And many of these experiments that I just showed the constraints for, so many of these experiments are observing a large number of low energy events in their low threshold detectors that cannot really be attributed to any previously known or previously thought of background mechanism for such detectors. So for example, I'm showing just one example here. So for an experiment like SENSE, which looks for electron recoils by measuring charge in their events, they saw something like this. So on the y-axis is basically number of events, you can say, and on the x-axis is the charge that is contained in these events. So you can see this large bump of single electron events, or events that contain just one electron charge. So SENSE, of course, was looking for these single electron events, but this very large number was surprising and couldn't really be explained by any previously considered background hypothesis. So this is just one example that I'm showing here. But several of the experiments that I showed already in the last slide have been observing this low threshold, low energy excesses. So our hypothesis about this, to explain this, which we put out in the paper in 2020, was that high energy particles, like for example cosmic muons, or even high energy electrons that can be ejected by photoabsorption of X-rays or gamma rays that can be absorbed in the detector. So these high energy particles that cross the detector, or even the material that is surrounding the detector, so they can interact with this material through very standard and very well-known processes, like for example Cherenkov radiation. And these processes can produce low energy photons. Then these photons can travel and can be absorbed to produce low energy electron recoil events. And our hypothesis was that at least some of the fraction of events that these experiments have been observing can come from this mechanism. So we take a concrete example at this point of the SENSE experiment at Minos Caverns at Fermilab, about 100 meters underground. So this is an actual image of the SENSE experiment. So for those of you who may not be familiar, so SENSE is an experiment that uses silicon skipper CCD to probe sub-GeV dark matter by a measurement of ionization or charge. So if a dark matter particle, for example, comes in and excites an electron from the valence band to the conduction band, then SENSE with its skipper CCD technology can measure even this single electron excitation in its detector. Now, not just that, but what SENSE has, it has excellent spatial resolution, or in other words, it knows where these events happen on these pixels that it has on its CCD. So as an example, I'm showing an image that actually Sensei observed in its recent data run. So the first thing that you see here are multiple bright white spots across the image, like bright white spots that you can see. So these are actually nothing but hundreds and thousands of secondary electrons that are measured by Sensei that are ejected by the high energy background that is coming in. So for example, this white track is nothing but a high energy muon that is passing through in the detector runtime, and on its way, it's creating hundreds and thousands of secondary electrons that Sensei is measuring. Similarly, you have high energy electrons, or you have about keV scale electrons that have been ejected by absorption of X-rays and so on. So these are the high energy backgrounds. But what Sensei is really looking for is just single electron, very low energy events, like single electron events. But you can also see these small white dots that are scattered across the image. So these are exactly the one electron events that Sensei is looking for in its analysis. So of course, some of these now, as you can see, some of the single electron events can be correlated with the high energy background. So using its spatial resolution, it knows the position information. So using that information, what Sensei does is that it places cuts based on the position of these one electron events with respect to the positions of these high energy tracks. So it removes a certain area around these high energy tracks that you can see, and counts the remaining one electron events in its analysis. So after doing this analysis and removing about 60 pixels, or that is roughly 900 micrometers area around these high energy tracks, Sensei still observed a very large event rate of about 450 one electron events per gram day, which was surprisingly high. And could not really be attributed to any known mechanism or any previously considered mechanism as a background. So what we pointed out in that paper could be happening was that these high energy tracks could be emitting Cherenkov radiation, and some of that Cherenkov radiation could travel away from these tracks and travel more than the 60 pixel or 900 micrometer, the cut that Sensei is applying. And they could be depositing these one electron, they could be absorbed to produce a one electron event, because they are low energy Cherenkov photons. So they will just eject one electron when they are absorbed. So of course, to test this hypothesis concretely, and to make a better estimate of how much this process is really contributing, we need a simulation which takes into account all the detailed effects. And that's exactly what we are working on right now. So this is a paper in preparation with the same group of people. So in this simulation, what we are trying to see is we are setting up the detector just like Sensei. And for example, a cosmic muon can come in. It can interact with the detector. It can emit a Cherenkov photon, and this Cherenkov photon can get absorbed in the detector to produce a single electron event. Alternatively, you can also have you always have like radio impurities in the materials that surround the detector. So you have X-rays and gamma rays that sometimes penetrate the shields and get inside the detector. So these X-rays and gamma rays very high in energy. So when they get photoabsorbed, they create high energy electrons. And this primary electron, before it loses its energy in its travel, it can also emit Cherenkov radiation, and then that can get absorbed to produce a one electron event. And this may not just happen in the instrumented part of the detector, which is the CCD, but for example, if a cosmic muon passes through an uninstrumented part, which is still a dielectric, so can have Cherenkov radiation in it. So some of these Cherenkov photons a fraction can pass through these layers and so on, and can also deposit a one electron event in the detector. So in this simulation, of course, because of time, I won't be able to go into all the details of the simulation that we are incorporating, but we are trying to take into account all the detailed effects as much as possible, like reflection at surfaces, refractions, and absorption, lengths of different media, and etc. Doping levels and so on. All these things play a part in the simulation. So taking into account all this, we are trying to estimate how much these processes are contributing to the event rate that Sensei observed. So just to show you an example of what we are seeing. So on the left-hand side is an image, a simulated image in our simulations of the high energy tracks, and on the right-hand side is the actual image again of what Sensei observed. So these are just the high energy tracks we simulated, and if on top of that I add the Cherenkov photons that have been simulated and the positions of the one electron events which they create, then I get something like this. So you see that most of the events happen very close to the tracks, but there are still some events, as you can see, which happen away from the tracks. And then these events can then lead to or contribute towards that 450 number that Sensei observed, even after applying the 60 pixel halo mask cut. So on these simulated images, we do the same thing that Sensei does. We do the same similar analysis. And after doing this analysis, what we are finding currently is that we can estimate the Cherenkov contribution to be about 150 events per gram day. There is, of course, some systematic uncertainty on this because some of the details like the absorption coefficients of some small layers and so on, there is still some uncertainty on what's the right values to use, how pure these things are, and so on. So there are some systematic uncertainties, but still it's roughly 150 events per 1 electron events per gram day. So it of course does not completely it does not completely explain this excess of 450 1 electron events per gram day that Sensei observed, but it's still even after including the systematics, it's a significant fraction. And what we wanted to point out, and what we will point out in this paper, is in any future versions of Sensei or in other detectors as well, we need careful evaluation for every detector, or a careful simulation for these processes where you can get these backgrounds, and people have to think about how to mitigate them very carefully. So with that, I'll move to the second part. And I'll talk about a background, a slightly different background that we estimated for the proposed detection methods of looking for single phonon excitations. So these will be signals in like milli-eV scale energy range, or tens of milli-eV energy range, and these will probe a sub-MeV dark matter. So the theory motivation remains the same. So even in sub-MeV dark matter parameter space, there are well-motivated targets. So there is again a freezing target in the sub-MeV parameter space. And if we plot sensitivity projections in these experiments, then assuming background-free kilogram-year exposure, so clean kilogram-year exposure in these experiments using these 3 different materials, then the situation seems very nice. I mean, it seems we can probe this freezing target in these experiments if we get single phonon sensitivities, which we'll probably get soon. But still, it's an important caveat to keep in mind that these projections are assuming background-free detectors. And it's important to estimate backgrounds in these future detectors, because if there are significant backgrounds, then of course these sensitivities, when you plot actual constraints from data, these change, and we might miss out on probing these very interesting candidates because of this. So in our recent paper at the end of 2021, we estimated one such background for these proposed searches, and it was a high energy photon background. So the photons that are coming in are high energy, and even in well-shielded underground environments, you always have these radio impurities which emit X-rays and gamma rays of the order keV to even MeV scales. So they can penetrate the shields and get into the detector. Most of the times what they do is they Compton scatter, or they get photo absorbed, and because they are keV and MeV scale, these will typically create signals which are very, very high energy compared to what these people will be looking for, which will be, remember, milli-eV scale signals. However, sometimes what these photons can do is these photons can give the atoms or the nuclei, the atoms, a small kick through coherent atomic scattering, which is a very standard, well-known process. And if you give a small kick to the nucleus such that the nucleus is not completely dislocated from its potential in a semiconductor, then this small kick will eventually lead to a collective excitation in the semiconductor, or in other words, phonons. And that's exactly what these people will be looking for in these experiments as a signal. So this is a background that can mimic the dark matter signal. So in this paper, we tried to estimate this background theoretically. So the way we did this from theory point of view is the following. So the cross section to create a phonon of energy omega from coming from X-ray or gamma ray of energy E gamma, which loses momentum q in the detector, is factorized into a coherent atomic scattering cross section, a standard process, multiplied by a structure function. So the structure function appears quite a lot in neutron scattering literature and has been borrowed in dark matter literature recently. So the structure function kind of intuitively incorporates or encapsulates all the gory details of the phonon dispersion relations and that information. In other words, it tells you the probability of getting a phonon in some final state, starting from an initial ground state, when you give some small momentum kick q to a nucleus. We found that this standard coherent atomic scattering cross section in the relevant parameter space is dominated by just the Thomson cross section of these high energy photons with just the individual core electrons that are bound to the nucleus. So there is a coherent enhancement with the number of electrons that are bound to the nucleus. So the picture is the high energy photon is coming in. It's scattering coherently with the core tightly bound electrons. It's giving the atom a small kick, and then this kick is transforming into a collective excitation or a phonon in the final state. And in the end, to get the final rate to create phonons of particular energy omega, we of course convolve this cross section with the photon number densities with photons of various energies, like X-rays and gamma rays of various energies that are coming in. So this just depends on what radioactive impurities you have in your detector, what their decay chains are, and what the impurity concentration is. So that determines how many photons are coming in, and so on. So for this, what we assumed was we just assumed measurements in a typical detector underground and in a well-shielded environment. And of course, there is an overall normalizing factor of the number of target atoms in the detector. So after doing this calculations and performing the estimates for 5 different target materials, which are usually considered for these searches, what we found was, so even in a very well shielded environment, so the photon background that I said we assumed was from the Edelweiss detector, which is a germanium detector placed underground and well shielded, like about 1500 meters underground or something, if I'm not wrong. So even in this very well shielded environment, this phonon background from the coherent atomic scattering of high energy photons could be as high as about 100 events per kilogram here, which is certainly not a small number. So of course, in all these searches, this background has to be carefully considered, analyzed, and mitigated, so that we can get sensitivities to these sub MeV targets that we love. So just conclusions about these background section of my talk. It's important to identify, characterize, and mitigate these new backgrounds in low threshold experiments to gain sensitivity to the theoretically well motivated candidates that we love and would like to test. So current low threshold experiments that I've already run and will improve soon, that have looked for electron recoils to probe sub-GeV dark matter, they could be already limited by backgrounds from processes like Cherenkov. Future experiments that will look for phonons may be limited by these coherent atomic scattering background that I talked about just now, coming from high energy X-rays or gamma rays. And now, once these backgrounds have been identified, there are of course some clear mitigation strategies one can perform So the first obvious thing is just increasing passive shielding, just put more shielding, putting more underground, and so on. So that will just mean less high energy stuff is going in. You have less high energy photons, muons, neutrons, etc. that are going through. So at the end of the day, these backgrounds, these low energy backgrounds are correlated with some high energy stuff that is coming in. So just increasing passive shielding will decrease these backgrounds. But also on top of that, you could also have like active shielding that is placed around the detector. So you could have, so you can actually identify when a high energy photon is going through, because that photon will typically leave some imprint through maybe a Compton scatter or something like that in the active shield. And if you have timing information in your detector, then you can throw away a corresponding or a time coincident low energy event that happens in the detector, because probably that high energy photon caused that event. So this will help veto those kinds of events. But our point was just to point out these backgrounds, and these backgrounds have to be carefully considered and mitigated in the future experiments. So that was the main part of my talk. Now, because most of you guys are neutrino experts, I would just like to end with brief thoughts about solar neutrinos as signals in low threshold detection experiments. So this is based on a paper I wrote with my collaborators in 2018. So none of us are actually neutrino experts here, like you guys. But the paper was actually about solar neutrino as backgrounds in low threshold detection experiments. And it was the usual story of like the neutrino floor and so on that many of you guys would have heard about. And it was just extending that story to sub-GeV parameter space. However, we thought, I mean, if you are at some point for high exposures in these experiments, if you're seeing solar neutrinos, then for a second you can forget about dark matter and just think about solar neutrinos as an interesting signal in itself, and think about what new neutrino physics or new solar neutrino physics you can do with these things. So I would just like to end with this. Oh, sorry. Oh, for some reason I cannot go ahead in my slides. So can I just stop sharing and start sharing again?
Yeah, maybe try that.
Yeah. Okay, let's see. Okay, here we go. Okay, yeah, sorry about that. Yeah, so what kind of signals we have from solar neutrinos in these detectors? So of course we have neutrino electron scattering, but because these solar neutrinos are high in energy, these leave typically very high energy electronic recoils of like 10 to the -1 MeV or MeV scale and so on, as you can see here. So these are not the kind of signals that these experiments are looking for. These experiments are really looking for EV scale signals, single electron recoils, etc. But these solar neutrinos also do coherent neutrino nucleus scattering, and that rate is shown as this solid black line here, and the contribution of different fluxes are shown as these dashed lines. Now, these are in the right energy ballpark of what these experiments are trying to probe. But of course, these are nuclear recoils, because this is neutrino nucleus scattering. However, when the nucleus is dislocated completely by a sufficiently highly energetic nuclear recoil, you always leave some energy in the ionization, a fraction of the energy. So this is typically called like ionization yield or quenching factor and so on. So these ionization yields have been measured for different materials, but typically for energies of hundreds of electron volt of nuclear recoils or even higher. So I'm showing just data for germanium here. But there is significant uncertainty in this parameter space of interest here, because this leaves about the right energy in electrons which these experiments are looking for. So to take into account this uncertainty, we extrapolated these ionization yields for 3 materials, silicon, germanium, and xenon, down to low energies. And for these three, for these three ionization yield schemes, we convoluted this with this coherent neutrino nucleus scattering events to calculate how many low energy single or double or three electron excitations these solar neutrinos can cause in these materials. And what we saw was in typical semiconductors, if you take a fiducial like the scheme in the middle, you need at least a few kilogram years of clean exposure, like no other background, to really start seeing these solar neutrinos. So these experiments are not there yet. You have like gram day or gram year kind of exposures in these experiments, but they will definitely get there at some point. And if these experiments are clean of any other background, then there is definitely a very nice and interesting possibility of seeing solar neutrino events in these low threshold detectors. And what one can do from this is, so this plot actually shows the different solar neutrino fluxes for a particular model. And these bands on top show what neutrino energy range that you can probe. This is basically threshold above which you can probe using single, double, and three electron events and so on. And for these three ionization schemes. So just assuming some optimistic scenario in silicon, for example, there is a possibility that one can look for these CNO fluxes, which play an important role in the solar metallicity problem, as they are very sensitive to if you have a high metallicity model or a low metallicity model. So one could just have a complementary measurement to the measurements that people already have. And also, one other important point is that these are coming from the method that is being proposed here is to look for ionization, but that ionization coming from coherent neutrino nucleus scattering. So the nucleus is scattering first. So this is basically neutrino flavor independent. This is a neutral current thing. So so you are basically probing or measuring all the neutrino flavors here. And if you do this measurement and combine with the Borg-Zeno measurement, for example, which looks for electron excitations and is sensitive to electron neutrinos, then that could be a direct measurement of electron neutrino survival probability in this transition region of a few MeV of neutrino energies. And as I understand, I'm not an expert in this, but as I understand, this is a transition region between the vacuum oscillation regime of the low energy neutrinos and the matter dominated effects regime at high energies. And so in this transition regime, it could be just a direct measurement or validation of the MSW theory. So one could possibly do these cool things using these low threshold experiments as complementary to the neutrino dedicated experiments like Borg-Zeno, for example. So with that, I think that's all I have to say for today. So thank you all for listening and giving me this opportunity. Happy to take any questions or comments. Thank you.
Thank you very much, Mukul, for this very nice talk. Yeah, so we can move to questions. Do we have any? Okay, George, I can see your hand.
That was an excellent talk. Thank you. It was great. So just, is there something one can do to other ways to mitigate the background? And maybe the answer is no because of statistics, but I'm just wondering about, for example, annual modulation, the way we used to, DAMA to look for an annual modulation in an otherwise noisy signal. But I guess you don't have that many counts, for example, in Sensei, when you subtract off, for example, your background. Any thoughts on that?
Yeah, of course. I mean, you could have, I mean, for the discrimination of background with the signal, you could of course use the annual modulation, and of course it's better if, for example, people are even thinking about like putting the detectors maybe in shielded environments, but in maybe outer space or on rockets, for example, or balloon experiments, which have much more modulation than what the terrestrial experiments observe. So of course, modulation is one way to do that. But in principle, just if you for example identify a particular background, so the way we have done here, like what the background is coming from, so then you can have particular mitigation strategies for a particular background. So for example, you have when you have Cherenkov radiation, the Cherenkov photons, these high energy tracks will emit Cherenkov photons in multiple directions. So for example, having like multiple detectors that have correlated time signatures or something like that. So when you see two events in two separate detectors, you know something is happening which is not dark matter. Then you can have active shielding, and of course, like trying as much as possible with radio pure materials and putting more passive shielding and so on. In the end, we should at least hope for seeing these low threshold detectors, which will have very high exposure and will only see the neutrino background in the end at these high exposures.
Thanks, Mukul.
Okay, thank you. Next question is from Kyle.
Hi, it was a great talk, by the way. Thank you. So I think earlier in your presentation, you talked about the spatial, or being able to see the events like where they actually happen in the detector. How is that actually useful? Because it's not obvious to me. I would think that you would just need the number of counts versus their energy, as opposed to like where they actually are.
Okay, yeah, let me go back to that slide. Yeah, for some reason I cannot again move the slides. Yeah, I don't know why this is happening. Sorry. Let me just stop sharing and start sharing again. Just a second. Sorry about this. I don't know why this is happening today. Okay. Yeah, so you were asking about the spatial resolution, correct?
Yeah, so like it's not obvious to me how that would be like a useful feature of the detector for Sensei, to like be able to have this good spatial resolution, when I would think you would just need the number of events versus energy.
Well, I mean, before you know about like any backgrounds or what is going on, when you see like when you see an image like this, for example, I mean, one assumption, and that's probably a fair assumption, and that works well for the Cherenkov photons as well, like the events created by Cherenkov photons as well, is that some of these one electron events could be spatially correlated with the high energy tracks that Sensei is seeing. And so to remove any correlated, like any one electron events that are correlated with these high energy tracks, this was a useful feature, and you can see actually that as in this plot, as you remove certain number of pixels around these high energy tracks, the remaining one electron event rate. So this is number of electron events that remain divided by the number of exposure that remains. So the rate of one electron events that remain actually drops off drastically. So this plot already indicates to you that one electron events are correlated somehow with this. So this excess of one electron events is correlated with the high energy tracks. Even for the Cherenkov photons, theoretically, typically in silicon, Cherenkov photons are distributed between like between the band gap or between the band gap and 3 eV or 4 eV. That's roughly the energy cutoff. And most of these photons will get absorbed very close to the track. So you can use this position resolution to get rid of these events. So the position resolution does help in this kind of detector.
Okay.
Does that make sense? Does that answer your
question? Yeah, it does. Yeah.
Okay.
Yeah. Thank you.
Okay, thank you. Next question is from Richard McDonald, I think.
Yeah. I have a question about the Sensei experiment, the picture that you showed. It looks to me like there's an awful lot more you can do in terms of radio purity and passive shielding. And quite frankly, I mean, a factor of 3 between your simulation and the data, I mean, it seems you may be able to bring that down by cleaning up by making sure the materials are radio pure and going deeper underground.
Absolutely. Yes, that is completely true. And so all this data actually that I'm showing here and all the analysis that has been done. So this is from the first run of the Sensei experiment in 2020, and that was taken at the Minos cavern. So this is the actual picture. But this is a relatively new experiment, and this was literally the first run that they had. They are definitely, as you are correctly, very rightly saying, they are definitely planning in their improvement to go even deeper. So this was 100 meters underground. So you still have some cosmic muons and stuff that is going through. So they are planning to do their next experiment at, for example, something like Snow Lab, which is like 2,000 meters underground. So where you will have even more shielding just from the overburden. And as you're saying, even the passive shielding around the detector, that will be definitely improved. So that less X-rays or gamma rays come in, more radio pure materials will be used, and so on. Yeah, I mean, yeah, you are absolutely right. I mean,
every material in there has to be checked for intrinsic radioactivity.
Absolutely, yes.
And
absolutely.
again, if you're using lead, you have to go to some ancient lead, because this is probably just lead bricks with lead-210 in it. And that gives you a continuum up to like 700 keV.
Yes, absolutely. So most of the experiments, you're right. I mean, many of the experiments know already, as you're saying, like what's the radio purity of the materials that you're using. So you can already estimate from the decay chains and so on how many of these things are coming in. For example, Sensei in its first run did not do this analysis. I'm sure they will do this when they expand. I'm not officially on Sensei. I'm just I just know many people who are. So I'm just saying things which I think are going to happen. But they are definitely going to do all these things. But you're right. I mean, you typically know how many of these things are coming in and so on. So in these simulations, for example, one could have used like a proper GANT kind of simulation where where you start from the photon itself and so on. But for example, in the simulation that we are doing currently, we just used whatever Sensei observed as the high energy background itself. To sort of guess how many photons would be coming in and so on. But that should be done as a measurement itself in the first place. You are absolutely right. But I think that will happen soon.
Thank you.
Okay, thank you. Next question is from Vic.
Yes, that's a really nice talk. I had to worry about the application of solar neutrinos because my observation is that the solar neutrino folks are a lot more advanced than the dark matter folks in suppressing low energy backgrounds. And just to give you a feeling for what Boraxino had to do to measure the CNO neutrinos, that required first a vessel that had 3 separate isolated volume elements to it, so that the outer shield the inner container. Just the point that was just made, the radio purities had to be maintained continuously. So at incredible radio purities of 1 part in 10 to the 18th, only sustainable because of the fact that you continuously purge the detector of contaminants that would grow in from the walls and so forth. And worst of all, even though Boraxino was a kilometer underground, the background rate it had in this region was a factor of 10 higher than the signal. And it took them years to figure out how to actually monitor that background rate. And the background rate is one that I think will come up generically in dark matter detectors too, that are particularly tricky. And that is, as a charged particle goes through a detector, it activates the detector. So the backgrounds are actually growing into the detector. And then you lose all correlation with the generating event, because the decay of, say, a beta decay or something of this sort occurs minutes or even hours later. And so the event is not correlated in time or position with anything that you can use to veto. In the case of Borexino, the deadly background was in fact the activation of a carbon-11 at a kilometer depth by the cosmic ray muons that were penetrating to that depth, and that was the thing that they, so debuting that is incredibly difficult. So you have to do all these steps that are not been yet really attempted in dark matter detectors. So that's why I think it's been really, really challenging. You had a comment in the first half though, and I was so wondering if you had done this calculation. When you're looking at the soft electromagnetic radiation that's deposited in a detector, one thing you know for most of these detector materials is the energy loss rate of charged particles as they go through. And you also know the cosmic ray spectrum that as a function of depth, even not only as the spectrum, but also as flux. So you can actually calculate the total electromagnetic energy deposited per unit volume per unit time. And then you can ask the question of, if I have 450 events in some detector, is that a large number of events, or is it a small fraction of the electromagnetic energy deposition? So that number wasn't brought out anywhere, but I think it'd be really interesting to know what fraction, for example, of these events might be associated with shrink-off photons, and how many are just, shake-off electrons and so forth that come from the fact that when a charged particle goes through material, it changes the local electric field. Have you thought about actually doing that calculation and then?
Yeah, absolutely. In this paper that we actually put out at the end of 2020, so that didn't at that point we were not really working on a specific simulation dedicated to Sensei or so on, and we just wanted to introduce or point out this background that this could be happening in the recent detectors. And at that point, we did like a theoretical estimate of like probably what you're suggesting of, because the depth of a particular experiment, how many cosmic muons are coming through, and so on. And we just did some theoretical preliminary estimates based on how far the particles will travel, how much energy that will lose. So the typical distance that a particle will travel. Based on its initial energy, how many, based on the energy loss function, as you said, how many secondary electrons it will create, and so on. So we did a preliminary estimate, and that indicated us that Cherenkov could easily give you like off the order a few hundred events per gram day, or 500 events per gram day, and so on. But the problem is, I mean, you really have to do a specific simulation for every particular experiment, because the geometric effects in these things are just too tricky to take into account by any theoretical calculation. So even in this simulation, for example, we are exactly taking into account all the things that you said. So when a particle is, so the cosmic muon flux, for example, we know at a particular depth what the flux is. So we are exactly using that many cosmic muons. We are just distributing their orientation. Actually, we even know the distribution of orientation. So we know at what angles these muons are going through. And then in this simulation, once a cosmic muon enters, for example, it has a particular starting energy, and then we know the energy loss function. And then that determines, so muons typically do not stop in the detector. They are too high in energy, but they cross completely through. But for electrons, for example, they lose energy and completely disappear. Basically, they lose completely all of their energy if they are low energy electrons, and so on. So yeah, we do take into account all these effects in the simulation.
Yeah, I think instead of calculating things event by event or process by process, using the fact that the local energy loss in materials allows you to get your define your sum rule. What if I find all the possible channels? This must be the total energy deposited, because this is the amount of energy that's being lost. So I think that would be a really interesting constraint on whatever you do.
Yes,
Thanks.
sure. Yeah.
Okay. Thank you. Do we have any other questions? Okay, I don't see more questions. So yeah, I'm going to stop the recording now, but if you have some more questions that you want to ask off record, or you can stick around for an informal discussion. Otherwise, yeah, thanks again, Mukul, for this very nice talk, and thanks everybody for joining.
No, thank you. My pleasure.